So today we're going to look at lesson 7-1. We're going to look at exponential models of growth and decay. So you're going to be expected to graph those, and you will have word problems associated with those. So the parent function that we are going to be working with is right here. Y equals A times b to the x. So really, I like to put parentheses here and here because the a should only be multiplied to this power b to the x after you've raised b to its whatever this exponent is. So you'll notice that this time it's unusual. We have our variable x in our exponent, and you see very interesting graphs here and here. So this particular graph happens to be y equals 2 to the x, whereas this particular graph is y equals 1/2 to the x. So our b here is 2 and our b here is 1/2. Our a is 1 because it's 1 times this power, 1 times this power. So there is not going to be any vertical stretch or shrink, so that a is that same thing that we've seen in all of our parent functions where it creates a vertical stretch or shrink, and if a is negative, it will reflect it. So this, I would add here that this is when b is greater than 0, or I'm sorry, greater than 1. You're going to have exponential growth. As long as this base here, and I'll show you why when we graph it, as long as this base here is a number greater than 1, you're going to have growth. The bigger x becomes, the bigger y becomes very rapidly. And if your base here, b, is going to be some number between 1 and 0, so a fraction, that's less than 1, you will have what's called exponential decay. You'll start high and go low. So let's write those on here. This is growth, and this is decay. So let's fill in our blanks here. Any function written in this form, where x is a real number, a cannot be 0, because as long as a is 0, this whole value here will be 0, and you'll just have the graph of the x-axis. B also needs to be greater than 0. So b can't be 0, it can't be negative, and b cannot be 1. So it's commonly called an exponential function, and as I said before, it's either exponential growth or decay. And the reason why b cannot be 1 is if I take 1 to any power, I will always have 1. So you'll end up graphing a straight line. So b is going to have to be greater than 1, and it's going to have to, and it could be between 0 and 1, or greater than 1, but it can't be equal to 1, it cannot be equal to 0. So I'm not really sure why she wrote that there. All right, so then when b is greater than 0, I'm sorry, when b is greater than 1, I've got that 0 on my brain, then the function is considered to display exponential growth. And so that's what you see on this particular one. So when b is greater than 1, we have growth. However, when b is between 0 and 1, then we will have exponential decay. And so the value of b in each case is known as the growth or decay factor. So b, and in fact I would probably highlight the value of b, so we'll highlight that whole thing, is known as the growth or decay, because that's really the one thing that's going to determine whether it is growth or decay. There is an asymptote, and so, whoops, let me get my pen back. Let's see if I can spell today. So there is an asymptote, and the asymptote that you don't see up here is right here. So on the parent function, the asymptote is y equals 0. There is no vertical asymptote. So your y values will always be positive in growth and decay, unless the graph has been translated. So that is a possibility. But let's just go ahead and graph this parent function that you see above. How did we get this function? So let's go ahead and go, let's move this down, and we'll look at this graph. So I've already chosen for you these values here. X can be positive, it can be negative, it can be 0. X is your domain, it is unrestricted. There is nothing that we can't put in an exponent. All right, so let's go ahead and write what we have. So I've got 2 to the negative 2, 2 to the negative 1, 2 to the 0, 2 to the first, 2 squared, and 2 to the third. So 2 to the negative 2, that negative exponent means it's 1 over 2 squared, which is 1/4. That negative exponent 2 to the negative 1 means it's 1 over 2 to the first, so it makes it 1/2. Anything to the 0 power has a value of 1, and this right here is called our key point. Very important point, we like to keep track of that. And then 2 to the first, of course, is 2, 2 squared is 4, and 2 to the third is 8. So we're going to go ahead and plot those. We're going to plot my asymptote first. All right, and then we're going to plot our points. So at negative 2, y has a value really close. I'm going to try not to touch that asymptote. And then at negative 1, we're at positive 1/2. It's a little bit higher. And then at 0, we're at 1. That's that key point. It's also our Y-intercept, so we can add that in here. It also, in this particular case, happens to be our Y-intercept. And on the parent function, the Y-intercept is our key point. And then when x is 1, y is 2. When x is 2, y is 4. And so you start to see y dramatically getting bigger as we go. And then 2 to the 4th, I guess we could put that on here too. Let's see, let's put a 4. So 2 to the 4th is 16. That actually fits on this graph too, so I am going to plot that in here as well. So you can start to see it really to take off. So let's connect those points. And here we go. And you know, it's that easy. Piece of cake. Let's make sure that we label a couple of values here. So let's label this key point as 0, 1, and let's label our asymptote as y equals 0. So we definitely want to have those labels in there. All right, so let's look at some characteristics of exponential graphs, which is our next slide. Let me make this a lot bigger. All right, so you're still going to have to talk about domain and range and asymptotes and all that fun stuff on here as well. And so as you can see, and as we talked about, your domain going from negative infinity to positive infinity, this graph is going to cover the entire x-axis. I can put any values I want to in for x, that exponent. So our domain is unrestricted, negative infinity to positive infinity, which means it's all real numbers. And it doesn't matter whether it's exponential growth or exponential decay, we still have a domain of negative infinity to positive infinity. And our range goes from low to high. So because of this asymptote here, our lowest y value approaches 0. Remember, y cannot be 0. I can't put a base of a number to an exponent that would give me 0. So the closest number that y approaches is 0 for our lowest value, and then it increases to positive infinity. So our lowest value here is 0, and then it goes up. Same thing if it's decay. Our lowest y value is still 0, and as we go up, this is approaching positive infinity. So again, it doesn't matter, growth or decay, and so all positive numbers, or all positive values for y. Okay, and then our asymptote is y equals 0 for both of those. Now that asymptote can move up and down. So of course, if we had y equals a times b to the x, and we added, let's say, a k out here outside the function, that k is going to move that y asymptote up or down, because if it's a minus k, it would go down. So bear that in mind. And of course, our key point that I already mentioned is 0, 1. That also happens to be the Y-intercept. And you might want to put in here that there is no X-intercept as long as the asymptote is on the x-axis. Okay? So as soon as that asymptote moves off of the x-axis, you could actually end up with an X-intercept. So it's possible. All right, so let's look at example 2. We are going to identify, just by looking at an equation, whether it's growth or decay. And we need to, so we're going to identify whether it's growth or decay, and then we're going to explain how we know, and then we're going to find the y-intercept. Remember that for the y-intercept, you are going to let the other value, x, be 0 to find that y-intercept. All right, so let's look at A. The main thing that I want to look at to determine if this is growth or decay is B. So right here, my B is 4. So since B is equal to 4, and that is greater than 1, then this is growth. Growth meaning it's going to start low and go high, right? So our y-intercept, we're going to let x be 0. So remember, anything to the 0 power is 1. So 4 to the 0 power is 1. So y is 3. So our y-intercept is going to be 0, 3. And that is our key point. And as you can see, A here is 3. That did cause a vertical stretch of 3, which is why that key point moved up 2 places. All right, look at this next one. 0.75 is where my focus should be. That's my B. All right, so since B is equal to 0.75, that's a 7, and 0.75 is less than 1 and greater than 0, that means decay. So I know that my graph is going to start high and go low. So it's going to look like that. And then our y-intercept, we're going to let x be 0. Okay, so anything to the 0 power is 1. So 0.75 to the 0 is 1. And so y is equal to 11. So our y-intercept is 0, 11, and that also is our key point. All right, so part C, a little bit more intricate. I'm going to move this up a smidge. So you were saving you saved $2,000 into a college savings account for 4 years. The account pays 6% interest annually. So your base is going to be your investment, whatever that was, plus 6% because the account pays 6% interest. This is what you ended up with. We don't know what we started with, but your base is going to equal your investment, which is called your principal. So whatever you originally invested, plus your 6% interest that you earned. So I don't know what your principal is, but it's going to be 100% plus your 6% interest, which equals 106%, and we have to convert that to a decimal. So remember, we always take the decimal point, which is understood to be there if you don't see it, and move it 2 places to the left. So it's equivalent to 1.06 for our base. Since 1.06 is greater than 1, we have growth. And hallelujah, you have growth, because you're investing. One can only hope that you have growth. All right, and so then your y-intercept is going to be so we're going to have to think about this a little bit. So if I let x be 0, that 0 for x represents x is your number of years, which you're going to find out here in a minute. X is your number of years that you held the investment, and you held it for 4 years. But if we let x be 0, that's at time 0. That's right when you put your money in the bank. So at time 0, so at time 0, which means x equals 0, your investment did not grow. So your investment is $2,000. So that is your y-intercept. So your y-intercept is going to be 0, $2,000. All right, well, let's go ahead and talk about interest and investments and growth, because this is actually important to your future life. So let's go ahead and look at the next slide. And I'm going to make this bigger. And this topic is near and dear to my heart, because you all should be saving and investing. All right. So your A of T is going to be your, well, actually, let's start here with A. We're going to start here with A, and we'll get to this A of T. So let's start here with A. That's your initial amount that you invest. So initial amount, and oftentimes we call this principal. Okay? And so it might be your starting amount, $100, $500. In the last example, to C, you invested $2,000 for 4 years. That $2,000 would represent this A right here. And then the R is your rate of growth. I hope it's not a decay. So rate of growth. And so your R has to be greater than 0 for it to be growth. I mean, I guess it could be decay. We could use this for decay. So if it is decay or decay, then your R is going to be less than 0. So it'll be a minus. So I mean, we could use this for decay. Typically, because I'm a financial person, we use this for investment purposes. But we could have a decline in a population, or it could be a stock account where you lose money instead of gaining money. So that is possible. All right, and then T is going to be your number of time periods that you hold your investment, or if it's decay, the number of time periods over which it decays. And we say number of time periods because it may not be years, it could be months, it could be days, it could be seconds. It just depends on what we're talking about. Then the whole A of T, which is our Y, that is going to end up being the final amount you have after T time periods. So you are expected to know this formula. So put it on a flashcard and learn it. All right, let's go ahead and use this formula. All right, so here we go. So I'm going to highlight a couple of things here as I go. So suppose you invest $500. So if I invest $500, that ends up being my A. So there's my A in a savings account that pays 3.5% annual interest. So that's going to end up being our R. How much? So I'm going to highlight that too, because that's what we don't know. How much will be in the account, and that's your total amount. So that's going to end up being your A of T, will be in the account after 5 years. So 5 years, that's going to be our T. So let's go ahead and input everything that we have. So A of T is what we don't know. Instead, and I'm going to just write out the whole general formula so we can see why I'm replacing with what I am. All right, so A of T we don't know, so we're going to leave that. Instead of A, we're going to put in that $500 times 1, and then because we are paying interest, that should be growth, so R should be positive. And then we have to exchange this 3.5% into its decimal form by moving the decimal 2 places to the left. So I have 0.035 all raised to the 5. I guess I could put that in red. I don't know why I chose blue, but that's 5. And of course, I don't like the way that looks. 5. There we go. So now you're going to use your handy dandy calculator, and you're going to run that through, and you're going to get, I'm just going to do one interim step here, so that gives me 1.035 raised to the 5th. So put that in your TI exactly as you see it, and you're going to round it to 2 decimal places because that makes sense for money value. So you'll get approximately $593.84. So over that 5 years, you got $93.84 for that small investment of $500. All right, so in example 4, it's asking you to do something different. It says if you invest your $500 that we just had above there, that pays your 3.5% annual interest, but instead of holding it for 5 years, your question is, when will the account contain at least $1,500? So that is going to end up being this, when will the account contain at least $1,500? That is going to be your A of T. That's your Y. That's your final amount. And so, and I guess the when will, we don't want to highlight that part, when will. It's not going to let me do that. Of course not. So this when will part, that's your T. That's our unknown. And so the $500 is still our A, and this is still our R. So in our formula here, A of t is equal to A times 1 plus R to the t. We are going to put the $1,500 over here equals, we know we still started with 500, and remember from our previous example that this interest rate converts to 0.035, and when added to 100%, it gives us 1.035, and then our t is what we don't know. So for right now, until you learn logs, you are going to put this into your calculator into your first y sub 1, and then you will put this into the y sub 2, and so you'll have two different graphs and they are going to intersect. So go ahead and stop the video, put that into your TI, and then restart the video and listen to what I have to say. Okay, so if you put this in your TI, it's going to look something like this. So this is your X and Y axes. So that's your X and your Y. And then this graph right here, so this Y sub 2 is going to look something like this. Okay. And then this is just a constant, so it's a straight line. It should be coming through here somewhere. So this is going to be a straight line going in this direction, and that's your y equals 1,500. What we want to find is this intersection right here. All right, so that intersection is going to be some x value, we don't know what, but the y value is going to be 1,500. So we want to find out at a y value of 1,500, what is our x value, which is our t. All right, so in your table or in your calculator, you can hit second, trace to get to the calc menu. And then under that calc menu, you want to select intersect. Right? So you want to find that intersection. So go ahead and pause the video, and I want you to run through that and find the intersection. Okay, so if you're having trouble, by the way, seeing this window, remember this is at 1,500, and your calculator naturally does a 10 by 10 window. So you need to go to your window menu, and I would change your X max to, I think I put 100, and your Y max, since this is 1,500, I put 2,000. If you don't see the intersection in your window, your calculator's not going to find it. So then when you do your second calc intersect, it's going to say first line or first curve, you hit enter. Then it'll pop it onto the next curve, you hit enter, and then guess, and you hit enter. And so you should have come up with a value of, and I'm going to round to 2 decimal places, 31.94, because there's a 5 that follows the 3, so it bounces that up to a 4. So that means that it will be about, if you hold your investment for 31 years, you're not going to quite get 1,500. So you won't get 1,500 until the 32nd year, because you have to get in that, you have to bump it up higher overall to get to enough to get there. So therefore, after 32 years, the account will contain at least, because it's going to be a little bit more, $1,500. Since interest is paid at the end of the year. And what that means, let's say that you invest that $500, you don't get your 3.5% interest until 12 months have passed. And then we can talk about whether the interest is compounding or simple interest, but you're not going to get paid interest daily. So that's why you have to wait until 32 years to get your interest for that partial year after 31, because after 31 years, you're only going to have $1,452.52. But after the 32nd year, you're going to get $1,503.35. So you have to wait till the 32nd year. All right, let's look at one last example, and we're going to look at population decay. So last. Okay, so in this particular example, we'll go through several steps to figure out, what we're going to do with the information that they gave us. So the table shows the world population right here of the Iberian lynx in 2003 and 2004, and you can see that it went down by 30. If the population is decreasing, so that's decay, in an exponential manner, and the trend continues, so the question is, how many Iberian lynx will there be in the year 2014? So there's a couple of things we need to figure out, and it does say to write the model as this, okay? And as you can see, this is the same model as A times B to the X. So A, our initial amount, so we're not investing this time, so this is our initial amount of lynx. And then our B is this 1 plus R. It's 100% of the population plus or minus the growth or decay. Raise the number of time periods held. Okay? So step one. Step one. We first have to find R. We don't know what our rate of decrease is. So to find R is going to equal the most current, I'm trying to think of how I want to put it, the most current population minus the previous population, all divided by the original. So it's new minus original over original, okay? And so this is new minus original over original. All right, so here we go. Let's plug in our values. So I'm going to take my newest population, 120, and then I'm going to put in my original population that we started with, 150. But we need to divide by our original, because what this is going to tell us is the change over the total original. So this is our part to whole. It's going to give us a percent. And that is going to end up being negative 30. Your sign is important because the sign determines that we have decreased in value, which ends up being negative 0.2. And you could put a 0 at the end or not, doesn't matter. So our R is negative 0.2. So then the second thing that we need to find is our B. That's our R. Okay, so our B is going to equal that 1 plus our R, right? So that's going to equal 1, and then if our R right here was negative 0.2, I'm going to put a minus 0.2. And so that equals 0.8. All right, and then number 3, step 3. Now I think we have, let's see, do we have everything we need? Our A is our original amount, which is our 150. And we found our B, which is our 0.8. And then X we have to find x, so we have to find our time period. All right, so let's go ahead and do that next. So we are missing our time period, so step 3, find, and they have an x here instead of a t. X and t are really the same thing. So we're going to find x. So let's say that our x is going to equal the years since 2003, because that was our original time period when we first counted the links. So x is going to represent the number of years that have passed since 2003. That's the number of time periods that have occurred. And so remember that y is going to equal our total population. Right? So to find our x, we are going to do 2014 and subtract the 2003. That is going to equal 11 years. All right, so now we're ready to throw all of that in our formula. We've gathered all the information that we can get. So I'm going to substitute everything into y equals a times 1 plus r to the x. So we have found that our a was our original amount, 150 links, or in 2003, times, and then in step 2, we found our b, which was 0.8. And then in step 3, we found our time, which was 11. Oh, see, look at all this down here. We don't need this anymore. We just did all that. Okay. So then you're going to use your calculator and run it through. And we're going to estimate, give or take. We're going to go to our closest year. And we get y is approximately equal to 13. Your actual answer was 12.88, but you can't have a portion of a link, so we rounded 12.88 to 13 because you can only have a whole number of links. And so to answer our question, therefore, if current trend continues, only 13 links will remain in the wild. All right, work on your homework. Text me with any questions.